All right, let's dive right in. We're going to peel back the layers on the invisible architecture that, let's be honest, runs our entire digital world. We're talking about network topologies. These are the essential maps, the blueprints that let all our devices actually talk to each other. Which really brings us to the big question that every single network designer has to face. It's a fantastic question, isn't it? You can't just throw a bunch of cables around and hope for the best. That would be absolute chaos. No, you need a plan, a specific design, and that design, well, that's at the very heart of what we're digging into today. How do you build a network that's not just fast, but also reliable and, doesn't cost a fortune? So before we can even start comparing these different blueprints, we got to make sure we're on the same page. What in the world is a network topology? To put it simply, a topology is the map of your network. It's the physical layout, the actual blueprint that shows how every single computer, every cable, and every other piece of hardware is connected. Think of it like a city planner designing a road system for cars. A network designer is doing the exact same thing, but for the flow of data. Okay, so here's our roadmap for this whole thing. We're going to start with the all-connected mesh, then move to the super popular star topology. After that, we'll look at a couple of single-path designs, the bus and the ring, see how they get all mixed up in the real world, and then finally, we'll talk about how you actually choose the right blueprint for the job. First up to bat is the mesh topology. And honestly, the best way to wrap your head around this one is to think of it like a direct flight system for your data. No layovers, no transfers, just a straight shot right from point A to point B. And when I say every device, I mean it. In what's called a full mesh network, your computer has a dedicated, direct cable connecting it to every other computer on that network. And that link, it only carries traffic between those two specific devices. That makes it unbelievably fast and super private. Now this is where things get a little wild. This simple little formula shows you how quickly things get out of control. See, with just 5 devices, you need 10 different connections. That's manageable. But remember our office from the beginning? With 12 computers, you'd need 66 separate cables. It just explodes. And this slide just perfectly lays out the big trade-off with a mesh network. On one hand, it is the absolute gold standard for reliability. If one cable gets cut, who cares? The data just takes another direct flight. There are literally no traffic jams. But, on the other hand, the sheer cost and the nightmare of installing all that cabling makes it completely impractical for most situations. Okay, so if mesh is basically off the table for most of us, what's the go-to alternative? Well, that brings us to a much, much more common design, the star topology. If mesh is that direct flight system, then star is the hub airport system, where all the traffic has to pass through one central point. Yeah, in a star network, my computer isn't talking directly to your computer. Nope. Instead, I send my data to a central box, usually a hub or a switch, and then that little box figures out where it needs to go and forwards it on to you. It's basically the air traffic controller for the entire network. And this really highlights the critical trade-off here. It's way, way cheaper and easier to set up than a mesh network. If the cable to my computer fails, it only affects me. Everyone else is totally fine. But it has one gigantic vulnerability, that central hub. If that hub goes down, the entire network goes dark. It is a massive single point of failure. All right, next up, we're going to look at a couple of older topologies that are built on a totally different idea. The idea of a shared path, a single shared road that every single device has to use. The first of these is the bus topology, which is just beautifully simple in its design. You've got one long cable, the bus, and every device on the network, computers, printers, whatever, just taps right into it. As you can imagine, this makes it super cheap and really easy to install. But hang on a second. This brings up a pretty obvious question, right? If everybody is sharing the exact same road, what's to stop 2 computers from trying to talk at the exact same time and causing a huge data collision? The answer is a really clever set of rules that basically boils down to listen before you talk. A device first listens to the cable. If it's quiet, it goes ahead and starts sending its data. But, and this is the key part, it keeps listening. If it hears another signal messing with its own, that's a collision, it just immediately stops, waits a random little bit of time, and then tries the whole thing all over again. It's a surprisingly simple but really effective way to manage traffic. So you can see that while the bus is super cheap and easy for, say, a tiny network, it has some major drawbacks. That main backbone cable, that's another single point of failure. And the more devices you add, the more traffic you get, and the whole network just slows down to a crawl. So our other shared road system is the ring topology. In this setup, each computer is connected only to its two immediate neighbors, forming a perfect circle. Data gets passed from one machine to the next, always in the same direction, kind of like a baton in a relay race, until it gets where it needs to go. Now, that one-way traffic flow is actually great for preventing collisions, and you don't need some expensive central hub. The problem, though, its weakness. It's a big one. If just one computer or one little piece of cable in that ring fails, the entire circle is broken. The whole network goes down. It's incredibly fragile. Okay, but in the real world, you almost never find these pure, perfect forms. Instead, what network designers really do is act like city planners building a huge metropolis. They combine different systems to create something much, much bigger and more complex. And this is what gives us hybrid designs. A tree topology, for instance, is basically just a bunch of star networks that are all linked together. It creates this hierarchy, kind of like a company's org chart. Or you might see a star-bus hybrid, where a bunch of individual star networks all connect to one shared bus backbone. It's all about mixing and matching to fit the needs of a specific building or a whole campus. Which, of course, brings us to the final and probably the most important question. With all these different options, how on earth do you choose the right one? Well, it all comes down to a balancing act. This table right here, it really lays it all out for you. Are you building a network where reliability is absolutely everything and money is no object? Mesh is your answer. Are you setting up a pretty standard office network that you know you're going to need to expand later? Star is the obvious choice. But what if you're on a super tight budget for a tiny, simple setup? Well then, bus or ring might just do the trick. It's always, always a trade-off between cost, reliability, and how easy it is to grow. So, at the end of the day, the most important thing to take away is this. There is no single best topology. It just doesn't exist. The perfect design for, say, a stock exchange where a split second of downtime could cost millions is completely wrong for a small coffee shop. It's always about picking the right tool, the right blueprint for the specific job you need to do. And that leaves us with a really fascinating question to think about. As our world gets more and more connected, as we build these massive, complex networks for smart cities, for the Internet of Things, for global communication, how are these fundamental blueprints going to be combined and changed and evolved to meet those unbelievable demands of tomorrow?